Welcome to Data Skeptic K-means clustering, the podcast exploring the problem, the algorithms, enhancements, and use cases for K-means clustering. As we heard in the last episode, finding the optimal answer to K-means problems is NP hard. This means that although we can't quite prove it, computer scientists are really sure this is a difficult problem. However, that does not mean that all hope is lost. Using established methods like Lloyd's algorithm, data scientists can typically find pretty good solutions in a reasonable amount of time. However, when the exact meaning of pretty good comes into question, it's time to look at other algorithmic approaches and their benefits. In this episode, I speak with Bernd Fritzsche about the breathing K-means algorithm.
My name is Bernd Fritzsche. I'm currently working at a German bank, and I'm in the financial sector since about 20 years. Before that, in the 90s, I have done research in academia in incremental self-organizing networks. And I recently, a couple of years ago, regained interest in neural networks and have done, as a hobby sort of, research in K-means algorithms, and have now written an article which is in the review state currently. And this article is called Breathing K-means.
Well, before we jump into K-means, what reinvigorated your interest in neural networks?
When I stopped working in neural networks, computers were slow and neural networks were difficult to train. You had to wait for a long time. And at some point, computers got so fast. And then around 2016, neural networks were everywhere in the press. One heard all these messages from deep learning, image recognition, and that was something new. And I was just curious, how good can they be? And did some course at Udacity in deep learning, although I have done backpropagation during my research time as well, but to get fluent in the modern technologies. And from that, I did not stop to keep on learning and also reopened my research from previous times and concentrated on the K-means problem, which I found very interesting already in the 90s when I first learned about it.
Does K-means have a lot of applications in your day job in the financial industry, or is it really a more academic interest?
K-means is actually used also in finance, not as a technique per se, which is a standalone, but as in many areas to get a grasp of the data and to do some pre-structuring of the data. K-means is often used to reduce the multitude of data items you have. So I recently heard of a usage also in our bank where K-means played a role. And K-means is everywhere. If people talk about data analysis, one of the first things you usually hear is K-means. And so it's a very ubiquitous technique, but it needs further techniques to be useful on its own. It's more a data reduction technique.
It's also one of the first techniques a lot of people pursuing machine learning pick up. It's sort of the archetypical example of an unsupervised learning problem, and it's pretty easy to use in libraries like Python's sklearn, so it wouldn't surprise me to find out most listeners just thought of it as kind of a done deal. Where are the areas that one might improve upon the standard vanilla K-means?
Well, K-means is very simple. You can explain it very simple what it does, but it is very easily ending in poor solutions and poor local minima. So the goal is to describe your data as good as possible with the least quantization error. And it is very easy to get a solution where K-means ends, converges, and there are much better solutions, but your algorithm doesn't find it. This was definitely the case before K-means++ was invented. So the standard K-means algorithm brings very different results each time you run it. K-means++ improved this a lot, but still you can easily come up with problems where also K-means++ regularly converges to solutions where the error is not at all minimal. And this is the goal, to describe your data as exactly as possible. And so you're striving for minimal error. The K-means problem is a very hard problem. It's NP hard, so you cannot reasonably find the optimal solution with a guaranteed algorithm. So it's interesting to find better algorithms that give you better solutions and more similar solutions, which are closer to the optimum, so that you have a better start for whatever you want to do after K-means.
I know this is a question that's maybe best answered with a visual, but we'll do what we can with the audio format. What happens when you get a bad result? Can we visualize that or think about what it is?
Well, a bad result is a configuration where you have particular centroids which have to cover a large number of distributed data vectors and create a large error. So there's a large distortion at these areas of the data space. It's difficult to visualize, but you see it in the numbers. And if you have a bad algorithm, it gives you different results of very different error values each time. That's one sign that your algorithm is quite far from the optimum.
And the k-means plus version that you'd mentioned, I know it makes its kind of improvement by selecting smarter initial centroids. Is that the same approach you take with breathing k-means, or is there some other technique involved?
No, what I'm doing is different, but actually very many variations of k-means try to improve the initial set of centroids. The very basic algorithm just takes a random sample from the data set and then runs generalized Lloyd algorithm starting from that data set. And k-means tries to find a better set by considering which centroids have already been selected and then select a centroid which has a large distance from all the existing centroids, and that on a stochastic basis, so it's randomized. But then, when this set of centroid is found, the normal Lloyd's algorithm runs, which is deterministic. It has these two steps, finding the sets belonging to each centroid, and then putting each centroid at the center of gravity of its set, and repeating this over again until the centroids don't move anymore. This is a completely deterministic procedure, and so everything is decided basically once the initial set has been found in these algorithms, like k-means or the algorithm based on a random sample. What I am doing and what other algorithms are also doing is to improve the set of centroids during the Lloyd's algorithm. Also intermixed with the Lloyd's algorithm, centroids are moved to avoid local minima. And that's a completely different approach, and it helps to find solutions which are of very high quality. But it's a completely different approach from just finding an initial set of centroids and then running Lloyd's. And that is what many other algorithms do, like splitting algorithms. There's the LBG algorithm, which starts with one centroid and then makes two centroids out of them, and then 4, 8, 16. And when he's done, then Lloyd's algorithm starts. And breathing k-means is different, as we see later in the discussion, that it does something to the centroids and moves them in a non-local way during or in between Lloyd iterations.
And that's the breathing step, correct? Or at least, I guess, the breathe-in step when you add more centroids to the existing set?
Yeah, the name breathing k-means comes from the fact that the number of centroids is not constant. It's k. We have k-means, so we want to have k centroids in the end. But breathing k-means adds a number of centroids and then reorganizes the resulting enlarged codebook or centroid set by the generalized Lloyd algorithm. And then it removes again, usually other centroids, to get again to k centroids. And this is repeated. And the number of centroids which are added and removed is diminished after a while. So at each step, at each breathing step, which is one addition of m centroids, then comes the Lloyd's algorithm, and then m centroids are again deleted. After each such breathing step, the overall error should be reduced. Otherwise, this number m is decremented by 1. So if you start with m equals to 5, which is the default value in the algorithm, then you take your k centroids, then you add 5 centroids, reorganize everything with Lloyd's algorithm, then you select 5 centroids which you delete, and then this centroid set is again reorganized with Lloyd's algorithm. And then you check the error, and if it's smaller than the previous time, then you repeat the whole procedure, and if it did not go down, then m is decreased by 1, so you then just add 4 centroids and remove 4 centroids in between each time a Lloyd iteration.
And do I do that just once, or?
That's it. That's basically the whole algorithm. It's actually very simple. It's the implementation using scikit-learn just consists of 68 lines of code. That's all there is. But there are some details which are not so obvious, in particular how to select the positions of the new centroids, and even more to select those centroids which you remove. One can make mistakes in that, and to avoid them, one has to calculate certain measurements.
Right, maybe let's focus on the first step. When we go to do the breathe in, I get the M parameter we're going to get from the procedure you described earlier, so I know how many to add. How do I pick where to add them?
That's quite simple. We want to reduce the error, so we can look for centroids which seem to have a hard time quantizing the associated data points. Each centroid has a number of data points associated, and we can just sum up the square error for each centroid and his associated data points, and then we have one centroid which has the largest accumulated error, so which has the hardest time quantizing his data points, sort of. And one could say this guy needs support, and so we put one of the new centroids right beneath him. And we do this for the 5 centroids with the largest accumulated square error. That's a breathe-in step. And the new centroids are not positioned at the same position as the existing ones, but with a very small random offset vector, so that in the next step of the Lloyd's algorithm, they are separated, and they basically partition the data set of these original centroids, which had a hard time quantizing their data. They partition these data sets into 2. And so these areas are now better quantized. Of course, we have now more centroids, and we have to get rid of them again, get rid of some again, to have our desired number k of centroids. And that's the next step. That's the breathe out step. But the breathe in is very simple. You just look for the centroids with the largest accumulated quantization error, and you put another centroid right beneath them with a little small random offset, and then you do generalized Lloyd.
So what's the computational cost in adding this step?
That's actually quite cheap, because before we do this, we run the generalized Lloyd algorithm. So the breathing k-means algorithm starts with a configuration generated by k-means plus plus. That's how I defined it. So we run the k-means plus plus initialization, but only once, not several times, as it is usual if you rely completely on k-means plus plus. Like in scikit-learn, by default, k-means plus plus is run 10 times, and the best result is selected because the results tend to vary. In breathing k-means, the k-means plus plus initialization is just done once, and then the Lloyd algorithm is run until convergence, and then the first breathe-in step kicks in. And after running Lloyd's algorithm, we already know which centroid has which associated data points. That's just a part of the Lloyd's algorithm to compute that. So we just have to add this, and then we sort the centroids by accumulated error and pick out the 5 ones with largest error and duplicate them, basically. So that's computationally very little. The computational cost basically comes from the fact that due to this breathe in and breathe out steps, we have to restart Lloyd's algorithm several times. And that's, of course, a multiplication compared to running Lloyd's algorithm just once. If you have the k-means plus plus algorithm in its simple form, you run the initialization, and then you run Lloyd's algorithm once until convergence, and then you're done. Unless you want to repeat this all over to pick from the 10 best, sort of. And in breathing k-means, after each breathe-in step and after each breathe-out step, you have to run Lloyd's algorithm. It converges usually pretty fast because you have done only local changes, some changes, only say 5 centroids have been added or 5 centroids have been deleted. So most centroids are already in their optimal position in the center of gravity of their associated data points. But those in the vicinity of the added or removed centroids, they have to reorganize. And that takes some Lloyd iterations. Not as many Lloyd iterations as one would need from a random configuration, but some. And this repeats, and that is where computational cost comes from. But overall, it's in many cases even less than k-means plus plus if you repeat k-means plus plus, since we do it only once. K-means plus plus needs to be repeated to have a decent result, and breathing k-means just runs once, and then the result is done. That's an advantage.
Well, I believe Lloyd's algorithm does, depending on how we set our stopping criteria, we know it's going to halt, but we get no real guarantees on the average amount of iterations or time it takes. It sounds like the breathing steps can speed that up in a lot of situations. Is there any way we can quantify that and know, maybe on average data sets, how much more efficient it becomes with the breathing step involved?
Already, K-means improves on the number of required Lloyd iterations. Of course, this initialization is already pretty good, and then Lloyd iterations don't have to move the centroids around so much. An even further effect comes from breathing k-means, but it's hard to quantify that. It's also for k-means it's not known how much iterations it will take. It depends on the data set, and the savings compared to running Lloyd's algorithm from a random configuration are not known exactly. But in experiments I've done, the k-means algorithm and breathing k-means have often about the same runtime requirement. So that's similar, but it depends on the data set, but it's in the same ballpark.
We could do some theoretical analysis, I suppose, and average over like the set of all possible data sets, but what I really care about is practical data sets that I might encounter in the real world, something that's going to come up where I want to deploy k-means. Are there any empirical ways you can compare the techniques?
I have done experiments mainly to compare to k-means. So I used a number of artificial data sets, which are well known and which are from some website which a researcher from Finland has set up, Pasi Frenti, which I will talk about a bit later because he has done several very good algorithms for k-means, which have very good results. And I also took the data sets from the original k-means paper for comparison, and they are high-dimensional, like 57-dimensional data sets, and in part quite large. And I used those data sets since there were already numbers available for them, and to make it not arbitrary. I wanted to not come up with all my own data sets because then people might ask, okay, here's just taking data sets which his algorithm just fits well, and I wanted to avoid that. I have not done now huge real-life data sets, but the algorithm has been tested on large data sets, and it works and performs very well also on large data sets. As I said, it's comparable to k-means in some areas. It's faster, and it's definitely a practically usable algorithm.
Yeah, those are the types of cases I'm interested in. If we just made random noise data, I don't know that we conclude much, but when we have data that has some underlying structure, those are the exact types of problems you would apply clustering to. So amongst those, well-studied types of problems where there is clustering available, you said on par with k-means++, could you share any, quantitative bits of that? Are there incentives that, because of the speed up, maybe you think people will more readily adopt? What's the real improvement that you get by adding the breathing k-means technique?
I was in the same ballpark. I just meant the performance. The performance with respect to computation time. The actual results are much better than k-means++. And I show this in quite large simulations that breathing k-means achieves a lower error by several percent, which is a lot in these k-means clustering problems. Depending on the problem, 3 to 10%, better than k-means++. Very reliable. I've done a large number of experiments, which means standard deviations, and so it's very significant that the results are much better than with k-means++. It's a large improvement over k-means++. I analyze in the paper also why this is the case. So what is a problem of k-means++? And the problem is basically that after the initialization phase, it cannot correct the initial positions. Lloyd's algorithm is only able to locally move around the centroids, but if you have several clusters and the number of centroids in each cluster is wrong, which you can see in some artificial problems where you select the data such that you should have, like, let's say, 3 centroids in each cluster. And if you do this wrong in the initialization, then k-means++ is unable to correct that. And the specific property of breathing k-means is that it can correct such errors. I could, in principle, put all centroids in one cluster of a multi-cluster problem, and then it would take quite a while. but Breathing K-means would move the centroids to all the other clusters until it has a fairly good solution. And the Lloyd's algorithm itself would only move a few centroids to other clusters and would leave most of the centroids in the original cluster, which is of course then very suboptimal if the cluster have similar density and similar number of data points. And that brings me to one topic, that it's actually very difficult to find fair test problems, because the problems you choose very much influence the quality of results. Some methods like K-means++ can work very well if you have a clear cluster structure with clusters of the same size and clusters of the same density. Then K-means++ works very well. If you have 16 Gaussians well separated from each other and you have k equals to 16, then K-means++ results are hard to improve. But real-world data does not look like that. Real-world data is sometimes not even visually clustered at all. It just has different data density in different regions. And the clusters are definitely not of the same size or of the same shape. Actually, as I also write in the paper in the beginning, I'm not so much interested in this paper in clustering, and K-means is, I think, not a very good clustering method. K-means is a method which distributes centroids such that an error function is minimized, or that's the goal at least, but this does not immediately lead to a good clustering, because clustering is often looked at as something perceptual. You see certain shapes and you think certain shapes belong to each other, or certain pixels belong to each other because they are part of a larger shape, and then you want to have these clusters identified. Well, that's a different problem than minimizing the error. And K-means, in its original definition, is just a way to distribute the centroids such that this error function, this quadratic error function, is minimized. And usually this does not give you a good clustering, because you do not know, if you have an unknown data set, how many clusters there are, and do not know anything about the shape and size of the clusters. So you cannot come up with a correct K, and maybe there is not a correct K, because you cannot describe, say, 3 large and 1 small cluster for centroids. That would just not describe the data very well. So K-means per se is not a good clustering algorithm. It can be the base of clustering algorithms because it distributes the centroids such that the data are approximated, but to actually form clusters from this is a different process. This is often confused, and the problems you see as example problems in books and software examples are often such that you have the same number of clusters, like 10 Gaussians, and you have k equals to 10, and then something happens, and in each cluster there's a centroid, and then it said, okay, the correct number of clusters has been found. But that's very artificial if you think about it. Real data does not look like that, and you do not know how your data looks like. And so I'm not looking at the clustering problem here with Breathing K-means. I'm looking at the vector quantization problem. So I'm looking at the problem to minimize this error. And one application of this would be actually vector quantization, to transmit a large data set of high-dimensional vectors over a thin communication line. And then you would like to have very good representative vectors, these centroids, so that you do not have to transfer the original data, but only for each high-dimensional vector, let's say a 100-dimensional vector, you only want to transmit the number of the reference vector or centroid, and then you get a huge improvement in data usage, which can be like a factor of 100 or something like this. So in this context, I see Breathing K-means. I'm not trying to find any clusters, any perceptual clusters. I'm just looking at this error function. One can use the results of Breathing K-means to find clusters, but one has to do something further than just a set of centroids is no clustering. This is often confused.
Thanks to our sponsor, mParticle. At the end of the day, your customer has to be at the center of everything you do. This starts with the right customer data strategy, as well as the right foundation to solve the challenges that typically inhibit success, such as data quality, data governance, and connectivity. mParticle is your real-time customer data infrastructure that helps you accelerate your data strategy by cleansing, visualizing, and integrating your customers' data from anywhere to anywhere. Ultimately, better data leads to better decisions, better customer experiences, and better outcomes. See why the best brands choose mParticle. Visit mparticle.com to learn how teams at Postmates, NBC Universal, Spotify, and Airbnb all use mParticle's customer data infrastructure to accelerate their customer data strategies. That's mParticle. Better data, better decisions, better outcomes. Visit mparticle.com to learn more. Yeah, I mean, I guess we would say they're implied by, is it the Verneuil cells or whatever, that those effectively define our clusters then?
You can make this, or you can see it like that, but I think it's often not very appropriate. You could have like two banana-shaped. One of my examples is a distribution from Yine. And in figure 8 of my paper, I have all the two-dimensional test distributions. And one looks like two bananas which are positioned so that they are quite close to each other, but are not actually touching. And as a human, you see two clusters, one with a larger density, one with a smaller density, but you cannot describe this with two vectors. If you say we have two clusters here and I set k to 2 and run k-means or k-means plus plus, then of course you end up with two centroids. But if you look at the data points which are associated with each centroid, then they do not describe those two bananas. They cut into these bananas and only take part of them. Each centroid gets parts of each banana, sort of. And so that's the difference between perceptual clustering and the result of k-means. With k-means, you have very hard borders, these Voronoi regions, which you get by measuring the distances, and they cut the space into convex areas, these Voronoi cells, and they don't care about any perceptual shapes you might recognize as a human. And to get this kind of clustering, where you have actually shapes connected and bending through the high-dimensional space, and you want to identify them, then you have to do more than k-means clustering.
Would that be something completely new and different, like dbScan, or could I maybe make some adjustment to k-means to get those intrinsic, intuitive visual clusters?
I think you can take the result of k-means and add a graph structure. There are ways to do this and then work on these graphs and try to find regions of high connectivity within this graph. And then you can actually find clusters which have also some perceptual meaning. But you have to use several centroids to describe one cluster. The identity one centroid is one cluster is only valid for very artificial problems.
Well, in going through your results from the comparison on the large data sets, it seems like overall we're getting more efficient results from the computational point of view, but also, as you point out, a much lower error. That sounds like a free lunch to me, but I know from the no free lunch theorem, there are no free lunches for optimization problems. How do you reconcile these two things?
Well, my algorithm has about the same computational requirements empirically as k-means plus plus. It depends on the problem. It can be sometimes a bit more, sometimes a bit less, but it's in the same range. I think this comes from the fact that I do not need to repeat it. K-means plus plus is usually repeated, often like 10 times as the default in scikit-learn. And this, of course, is costly. And on the other hand, Breathing k-means needs to do quite a number of Lloyd iterations. So this is also costly. But in the end, it averages out. So what the time k-means plus plus spends on repetitions, Breathing k-means spans on additional Lloyd iterations. And so the computational effort needed is about the same. I write in my paper, in the current version, that this is likely a new state of the art. This is probably something which I have to take back, because state of the art is a very difficult topic for k-means, because k-means is in principle enumeratable. If you have a finite set of data points and you have a certain k, then there is a limited number of a high but limited number, a finite number of ways you can distribute the data points to the k-centroids. And so in principle, you could just go over all possibilities and find the global optimum. And so it's hard to say something about state of the art if you do not take into account how much compute is necessary to do this. It's of course not practical and it's an exponential effort, but in principle it's possible. And so for k-means, one probably cannot even say this is the state of the art. So in the next version of the paper, this will be expressed differently. Among the practical algorithms, I think breathing k-means, so which you can apply to practical data sets, is one of the best or even the best. One reviewer has pointed me out to the work of Pasi Frenti from Finland, and he has two very different approaches which also have very good results, are also better than k-means plus plus. One is a simple random swap algorithm where he just randomly swaps centroids and does Lloyd algorithms in between without actually looking which centroids to swap. But this works amazingly well, and he gets results better than k-means plus plus with this. And the other one is genetic algorithm, where he copies principles of evolution in a problem-specific way, which also gives very good results. And I'm currently in the process of comparing the results of these algorithms to Breeze and k-means. For the two-dimensional problems, these two algorithms are in the same performance range and the same quality range than Breeze and k-means. So they are all better than k-means plus plus. For higher dimensional data, and in particular data where you have different densities in the clusters, I so far detected that these other algorithms have difficulties, but I still have to verify this. So as I said previously, it depends a lot on the kind of problems you look at. And it would be good to have some sort of standard set of problems where you can compare algorithms to each other in a rather objective way, like in the image processing or in the image recognition area. For some time, ImageNet had this role, a large database of images where the recognition results could be compared in a normalized and controlled way. And that led the field ahead quite a bit because this made it objective to compare different algorithms. And the problem with any new k-means algorithm is that there is no such benchmark set currently for k-means. So everyone runs in the problem of choosing problems which are suitable only for his own algorithm. I try to avoid this by taking mainly problems from the literature, and I think this is a necessary approach. But I was surprised when I looked at these two algorithms, which I received from the review from my paper, that they have such good results, and I will overwork the paper and include these results and check whether they are actually general. Currently, I have the impression that there are classes of problems where these genetic algorithms and random swapping fail, in particular if you have different densities, but I'm still in the process of checking that. It's too early to say. And then I will resubmit a revised version of the paper.
Well, it'll be good to see. I'm very curious to hear how the comparison winds up. There's certainly a lot of good work going on in k-means right now. And I like your suggestion for a standardized data set. I think that's more than overdue.
I have most of my examples from a web page which Pasi Frenti has set up, and his group is doing most of the work in clustering and much work in k-means, and he has written a large number of articles on this. Maybe I can convince him to more formally set up such a standard set of problems. I think the area of clustering research would benefit from this if this could be done. And he has already done activities in this direction, but maybe a more formalized way of trying out algorithms in an automated way on a number of problems so that you have a ranking list or something like this would even be better. I think that would be a very good idea.
Well, we know there's a very large set of possible data sets one might try and apply clustering to. Are there any formats of data you can think of that might be adversarial to your approach, or a situation where you wouldn't want to apply breathing k-means?
In general, clustering algorithms work in high-dimensional spaces, and if you use Euclidean distances, then you are obviously depending on the scale of the various axes. So scaling can change results quite a bit. And you need a metric in these spaces. So if you have data which is just nominal, like certain qualities, colors or something, or other attributes which are not sortable on some linear scale, then you cannot do k-means in a direct form. You can do a one-hot encoding to simulate this in some way, but k-means is best applied to purely numerical data, which you can sort in any direction, and where you are confident about the scaling of the different axes. If you put together different attributes then it depends on the units, what you get for numbers, or the units influence the numbers you get. And of course, this is an important pre-processing step, and your error may be influenced in one or the other direction, depending if you measure things in meters, centimeters, or millimeters. So this is one thing one has to consider when using such distance-based algorithms as k-means. There is no automatic scaling.
Good point, yeah. Well, usually at this point, before I do any kind of wrap-up, I like to ask, is there anything you think I should have asked you about that we didn't get to?
There's one thing, perhaps the one core point about the algorithm is the choice of centroids to delete. And that's actually perhaps the most important point of the algorithm. Inserting centroids is very easy. We were just looking for the centroids with largest accumulated error. However, deleting centroids is a quite different thing. The measure I'm using there is the utility, and utility is defined, that goes back to some work I've done in 1997. That's the increase in error which happens if you delete a certain centroid. So if I have a certain centroid set, then it has an associated error for this data set. And if I take any centroid away, then I get a larger error, because now these data points which have been quantized by this centroid are quantized by further centroids, by more distant centroids. And so one can say, okay, the utility of a centroid is this increase in error. But it's not that easy, because the utility of centroids which are neighboring is very small. If I put one centroid in the vicinity of another centroid, at some point I can take away one or the other, and the overall error would not change much, because they are so close to each other. They are able to take each other's data points without any large error increase. So it is not sufficient to look for centroids with low utility, but you also have to make sure that you do not remove neighboring centroids at the same time. And since I'm removing several centroids, like 5 or 10 or 20, I have to be careful not to remove neighboring ones. Otherwise, I would get a huge increase in error. And to ensure this, I have introduced a technique called neighbor freezing. I'm sequentially selecting the centroids I want to remove, and I freeze the direct neighbors of the centroids, which are the nearest neighbors. I freeze the nearest neighbors of each centroid which I remove, and they are spared from removal in this freeze out step. That is a very crucial technique to ensure that we do not have a large error increase during the breeze out. The breeze out step always increases the error because the number of centroids goes down. But by doing this neighborhood freezing, I can minimize this increase of error, and so overall let the algorithm find good positions. In the breeze in step, I'm looking for high error centroids and enlarge them or support them with additional errors. And in the breeze out step, I take centroids away, but I avoid taking neighboring centroids away. And this is basically the secret of breathing k-means, that it works. If one would just remove those with little utility, then one would have a big up and down of error values and probably convergence problems. By introducing this neighborhood freezing, this can be avoided. So this is a very important detail of the algorithm.
Yeah, when I was first getting familiar with it, I was reminded of techniques like simulated annealing, or maybe the decaying learning rate we use in neural networks. But this nearest neighbor freezing seems like a novel step. Is there any precedent for that, or is that a unique feature of the breathing approach?
To my knowledge, it's new, and the whole algorithm is very goal-directed. If you have simulated annealing, then you introduce energy to the whole system, in the beginning large, and then lower the energy level. It's a very general search technique, which throws everything around in the beginning when there's a high energy level. Breathing k-means makes very selective steps, both in the breathe-in step and also in the breathe-out step. So it's very goal-oriented, and the criterion is directly the error function. So the breathe-in step directly looks at the quantization error, and also the breathe-out step directly looks at the quantization error and tries to avoid any large increase in the quantization error. And that makes it very different from any random search. It's very goal-directed, and that leads also to a very fast decrease in quantization error during the run of the algorithm. If you look at the error curves, they drop extremely fast because in the beginning, like centroids are moved to completely different areas where they make a huge error reduction. And that's the point where local minima are left, or the algorithm leaves local minima by sorting the centroids in the right way among the clusters. And it is greedy in a way that the movement go to those areas where there is most error to reduce. And that leads to very quick reduction of error. And you can often also stop the algorithm after a few steps and have already a large error reduction. And you can start this process also from any configuration. If you have a solution from k-means++, which you have perhaps selected or from any other source, then you can give this solution as an initial configuration to breathing k-means, and with a large chance, breathing k-means will be able to improve upon this solution directly without any further initialization. It's a solution improvement technique. You can optimize or improve any given solution in the limits of this algorithm, and due to its non-local nature, there's often ways to improve the given solution where the previous algorithm ended in.
Makes sense, definitely. Well, one of the things I really appreciate is when I get a paper that I enjoy and it comes with some code. Can you tell me what it'll take for listeners to get up and running trying your technique on their data?
That's trivial, basically, because I created a PyPy package. It's called bkmeans, and you find it on PyPy. So you just do something like pip install bkmeans, and off you go. If you go to the package, there are two little example programs. The API is basically copied or stolen, you can, as you like it, from scikit-learn. They have a very good API for their k-means class, and I basically took this API. The implementation of breathing k-means is also based on scikit-learn's k-means class. That's the reason why it is so short. It's only 68 lines of code, and it derives from the k-means class from scikit-learn. It just adds this one additional parameter m, and otherwise all other methods are the same. They are inherited from scikit-learn. So everyone who has used k-means from scikit-learn can, with the same calls, use breathing k-means. He just has to write bk-means instead of k-means. And since the parameter m has a default value, he or she does not even have to set m, just can use the default value. In my paper, I described that taking larger m's gives even better solutions, but with m equal to 5, the default value, you usually get very good solutions. It's extremely easy. Everyone who has used scikit-learn before and k-means there can, with the same API, use breathing k-means. I'm currently thinking about also providing a version for R. That's a big contender of Python in the data analysis space, and the k-means version, which is the default in R, is the Hartig and Wong algorithm, and that's a completely different algorithm. And I also did some experiments, and the Hartig and Wong algorithm is for those datasets I applied it to inferior to the breathing k-means. And k-means plus is not very popular within our community. So I'm thinking about also providing an R package if I find the time, so that also in this space the algorithm is available. So it's very easy. If one wants to try it out, it's extremely easy. You don't have to use any GitHub or so. You can just pip install the software and try it out.
Sounds good. Well, Baron, thank you so much for taking the time to come on Data Skeptic.
Many thanks for having me. It was a pleasure.
That concludes another installment of Data Skeptic K-means. Thanks to our sponsors today, mParticle. Myself, Claudia Armbruster, as associate producer, Vanessa Bly, guest coordinator, show notes written by David Abembe, and our host, Kyle Polich.